out whether the object present in this image is dog or not. Now you take a situation, assume a situation where you are left in a dark room. Right now you are searching for an object in the dark room. What will you do? You will take a torchlight or a flashlight, go to the room and look for different positions of that room. Right? So when you lit your flashlight, what will happen? Not all the room will be shown to you. Only a specific portion of that room will be shown to you. Right? Now this situation can be compared with our situation. The entire image is equivalent to the entire dark room in which you are going to search. Your torchlight, which is useful for searching, is nothing but the function G, which is nothing but the filter or the mask. Right? In that specific position, what will you do? You will search in another portion. Likewise, till you find the object, you are going to move your torchlight throughout your room. The same process is going on inside the convolution also, right? So what happens is that flashlight can be called as a filter or a mask, which is again going to be a small matrix, right? Small matrix, maybe the size 5 x 5, or you can say 3 x 3 or 4 x 4. Anything is fine. That depends upon the user. Now this 5 x 5 pixel is called as a filter or a mask or a kernel, right? It is related with image processing stuff. Now what you are going to do is you are going to overlap your filter on the image. Right? Remember, this mask or filter is not an image, right? It is a simple matrix with very low values. Right? So they will be multiplied and they will be added together. When you multiply and add together, what will be your answer? You will get a single value, right? Then what you are going to do, you are not able to find that object in that specific area. Now you shift your location a bit. Again, another 5 x 5 region will be overlapped. The filter remains the same, but the position in the image will vary. Now you will get another number. So if you keep on moving your mask over the image, you will get different numbers, single number. So if you are moving for 784 possible locations, right, then you will get 784 single numbers, which you can convert into a two-dimensional matrix. 784 single column, convert it into a two-dimensional matrix where you will get a 28 x 28 size array. This is an example, right? So this 28 x 28 is called as a single sub-image, right? Now, I want to have another sub-image. I am unable to find the object from that specific torchlight. What will I do? I go, keep this torchlight, take another torchlight. When I take another torchlight, the clarity may be high. The size of the flash portion may be high, right? So the parameters may change. Then I will get the same process will be repeated. Then I will get another sub-image. Right? So depending upon the number of filters you are using, you are going to get different small images. Now can you compare how the child's image is broken into different small sub images? I'm sure you can do that. This is the mathematical illustration for that. This blue color is the original image where some values, these are some example values, is given there. Now this red color, take the first red color box, 3 x 3 box, which is the filter. Right, so I'm just overlapping with the position of the one position of my original image. So the pixel values will be multiplied 0 into 1. Locations were there. I was able to get 9 single numbers. When I convert into 2D matrix, I will get a 3 x 3 matrix. Now if I take another filter and overlap on the image again, I will get another sub image or sub. So for visualization, you may get something like this. You have a car image. This is the original image, but this original image is divided into many small sub images in the first layer of your convolution neural network. You can see there are 10 small rectangular boxes. So 10 sub images you have got. What do you see in this each sub images? No much information, but you can see some shades, some lines, some curves. right? Some variable intensity values that you can get. Now the interesting aspect is each subimage is called as a feature descriptor. Now can you correlate with the statement which I gave in the initial introduction slide, need for deep learning approaches? I told you the feature extraction is done automatically, not manually, right? So this is one step, or we can say the convolution actually does the process of feature extraction, right? Does the process of feature extraction. Each small box can be called as a feature, right? Now we'll take this as an example for a first convolution layer output, right? I have done one set of convolution process and I have got this output, right? The filter is given here and this line is given here. Now I'm talking about an animal. Can you tell me what animal I'm talking about? Anybody want to take a guess? You can unmute and let me know. Anybody want to take a guess? What am I talking about? You may not, right? You may not, because this information is not sufficient to identify whether this is a tiger or a lion or a giraffe. Most of the animals will have this information, right? Actually, I was talking about the back portion of the mouse. Right? When I overlap my filter with my original image, this portion is visible for me, not the complete portion. What do I mean to say? The output from the first convolution layer is not sufficient for identification of the object, or I can say the information which I got from the first layer output are called as low-level features, from which you will not be able to identify the object. So what should you do? Do one more convolution. That's why I told you there's a problem. I do not know how many convolution layers should I have. Do one more convolution. When you do more convolution, you can find that you will get higher level features. So more convolution means more layers. Now can you correlate it with the first information I gave you? More layers corresponds to more accuracy. So more the number of convolution layers you have, the better will be your object recognition capability also. Right? Say for example, what are these higher level features? Maybe the paws of the cats, the claws of the eagles, the beaks of the birds may be called as higher level features. Or in terms of shapes, you can say that square. What is a square? Square is formed from 4 straight lines joined at 90 degree or some degree, right? So a single straight line may be output of one convolution layer. When you give that as input for the next convolution layer, there is a high chance that you will get the continuous region. So when you finally find a square, you may get at least some idea. Okay, it may be a box, or it may be a table or something which is in the shape of the square. This is how the machine, the CNN, is going to identify or recognize what object is there in your picture or in your image. Instead of myself extracting the features, it is going to extract the features on its own. Now, I have many convoluted child's information, right? That means that subimage is not necessary for my further processing. When I finally give it to my fully connected layer network, it doesn't have any information. Already my network is going to be huge. Why should I again burden my network with an unwanted image? So what I can do is I can remove those subimages which doesn't have any useful information. How do I find that? How mathematically is done? You do the convolution process, that is multiplication and addition, and whenever you find a smaller value, look at the rectangular box of the second diagram on the right hand side, you can find that the value is 0. Right? Whenever you find a value of 0, then you can easily identify there was a mismatch between the filter and the object. Right? All other values are 0, then multiplied with 0 is going to be always 0. So you can remove the subimages which gave you a value of convolution value of 0. Right? So this is how we can identify whether this subimage is useful or not. So we are going to reduce using the downsampling technique. This downsampling technique is called as max pooling. So max pooling, how can you do this downsampling? You can take and arrange 4 subimages in a single quadrant. You can take 4 subimages and arrange in a single quadrant. You can see the yellow color dots. These yellow color dots corresponds to the 4 subimages, among which the circled one is the one which with the highest possible value. Highest possible value means more information. So I am going to take it for my further processing, right? So 1:4 is chosen and the remaining 3 are eliminated. But this 1:4 is my choice. You can go for 1:2, 1:6. That is up to you. So max pooling just do the process of downsampling, nothing else. This further reduces the dimension of the data. Now you are going to give it to the fully connected layer or the artificial neural network. So you must have a thorough idea on the training process of normal neural network. It is a normal ANN with many layers which requires training as usual. How do you train the convolution neural network? Now you understood that you have convolution layer, you have max pooling, you have fully connected network, right? So how do we train that process? So we have a forward pass in which first the filter parameters are also called as weights are randomly initialized. In the normal neural network, you will have only the concept of weights between the hidden layers. But when you look at your convolutional neural network, you will have the filter parameters also. They are very, very, very important, right? Based on the filter parameter size, you are going to overlap. So when the filter parameter specification changes, it will also change, right? If the clarity is good, you may find the object. If not, you may not be able to find the object, right? So we have 2 sets of parameters to be adjusted in CNN, which actually is the reason for the heavy computational complexity of CNN, right? The filter parameters should be adjusted and also the weights. Both are randomly initialized in the first stage. Using these weight values, as we know, we find the convolution layers. Then we repeat for many convolution layers. If you have more, then you go for the max pooling layer. Once you complete the max pooling layer, now you are going to pass on to the fully connected layer. But here you need to understand that your max pooling layer output is in the form of a 2D matrix, right? But your fully connected layer, I showed you a diagram where the first layer is in the form of a single column. So your 2D should be converted into a 1D dimension. Once you do this process using a flattening operation in Python language or anything, right, you can convert into a single layer. Come back in the reverse pass. So in the reverse pass, your weights of the fully connected layer will be adjusted first using a mathematical equations and expressions are available, and then we go for adjusting the weights filter parameters. Once these 2 parameters are changed, again the forward pass will take the reverse pass, and this iteration will keep on going. You must have a thorough idea on that. That's why I told you in the initial slide itself, try to have a good knowledge on artificial neural networks. You can refer some of my YouTube videos which I delivered a talk in other institutions, right? Or you can refer this good book, Lauren Fawcett or a cow or whatever it may be. So this is a small mathematical step. Maybe due to lack of time, I will just skip this. Mathematical steps are very, very important, right? Deep learning is all about computer science plus maths. People are very interested to go for deep learning, but they hardly show interest in studying or learning the mathematical concepts, right? It's very, very important. And research papers, when we look at the research papers submitted for our journals, first thing is we look at how much amount of mathematical equations are there in the paper, right? Engineering is all about maths, but deep learning papers hardly have any mathematical equations within them. The reason is all these mathematical equations which I am showing you now is available as a simple tool in the Python language. So why should they go for programming this? So they do not pay attention. That may not be necessary, but to make some changes, you must have a complete understanding on this mathematical equation. This is a simple filter and an input, and you will have an output. and your one overlapping process, your output is shown as a combination of your normal multiplication and summation. Multiplication and summation. Convolution is all about that. So when you go for O11, O12, O21, O22, depending upon the number size of your filter, and this is the way how the filter parameters are adjusted. All right. Your output layer is very close to the filter parameter is. You look at the left hand side of my screen. Dou L by dou F is equal to dou L by dou O into dou O by dou F. Dou L by dou O is the actual loss function differentiation with respect to the output value at the output layer. The other one is at the filter layer or at the convolution layer. We make use of chain rule of differentiation, right? Whenever you study deep learning or artificial neural network, you will have differentiation, right? The reason is we want to make the error equal to 0, right? To make the error equal to 0, suppose if your values get trapped in a constant value, let's say for example 5, your error is a function initially, now it drops down to 5 or 10, some numerical value, right? Only if you differentiate that value, it will be made equal to 0. What I showed you, feature extraction and again classification. But the only difference is feature extraction is automatically done by the network itself in the guise of convolution and downsampling or your max pooling. Once these features are extracted, again we go to the normal process of classification. That's why I have given represented in terms of a blue color box and a red color box. Again, we have many combinations, many softwares are available. MATLAB is available, Python is available, R language is available. Depending upon your efficiency or depending upon your expertise, you can use anything. I have worked with MATLAB and also with Python. So I think anything is okay for me. But suppose if you have already known Python, MATLAB only, you can still do your process with that. One of my scholar has done only with MATLAB toolbox, right? I think it is a 2018 version. Right? I'm sure it is a 2018 version. But if you know Python, I will advise you to go for Python because it is more user friendly when you go for multiple layers. Requirements, a high-end processor is very good. If you have a higher specification, it is very good, but you must have a sufficient bank balance for getting a good system also, right? If your university provides that, very good. But otherwise, some of my scholars are only using their laptop to get some of the results. So it depends upon you. Now we go into the last session of our part of our topic, transfer learning. Right? One drawback I told you in CNN, I'm not sure whether you have observed that or not. How many convolution layers should I have? How many normal max pooling layers I should have is still a problem, right? And the second problem is the computational complexity. I need to adjust the parameters of the filters and also I need to adjust the parameters of the normal fully connected layer weights. Can I make it more simple? Can I fix the number of convolution layers? Can I adjust only one weights instead of going for filters and the normal weights, right? The answer is transfer learning. First, we will see what do you mean by transfer learning. Then I will associate transfer learning with the CNN process. Human beings always have the capability of transferring knowledge from one task to one domain. Say, for example, if you know cycle riding, you will learn how to drive a car. Right? If you know cycle riding, you will learn how to drive a car. That doesn't mean exactly that both are same, but you are transferring some knowledge. What knowledge? You know, you have to apply the brake to stop the vehicle, right? You know when to turn, how to accelerate, right? So this knowledge you know because you have already used the cycle with you. So when you go for a car, the process may be easy. You can take some knowledge, some previous experience from the previous action and pass on to the next action, right? Now, if you take this statement, riding is a word, or maybe you can say drive a car. Driving and riding, both are same, which corresponds to the same task. The task is going to be same. The work is going to be same. But what about the domain? The database, they are different. One is cycle, a non-motorized vehicle, and the other one is car, which is a motorized vehicle. So what actually you are doing the same task, but you are transferring some knowledge from the first task on a domain to another task on the another domain. Based on the task and domain, you can have 4 possibilities. Same task, same domain, same task, different domain, different task, same domain, different task, different domain. Option B and C is the important one, because same task, same domain, anyone will do, right? There is no necessity for transferring more knowledge. Say, for example, I am writing an English essay. I am writing an English poem. If I know English, writing an English essay, there will not be a big deal in writing an English poem, right? Or when you take the last option, different task, different domain, there is no necessity for transfer of knowledge because both are different. The important one is same task, different domain, and different task, same domain, right? Classification of brain images and classification of lung images. Same tasks. This is what transfer learning is going to do. Maybe this is an example. I can skip this, right? How can we do this? How can we do this? Right. So look at the diagram on my left hand side, where you can find that 2 data sets are available. Data set 1 and data set 2. Say, for example, data set 1 is brain image. Data set 2 is lung image. Right. But when you go for the classification and segmentation process or any process, you need a large amount of database. That's what you would have heard if you're using deep learning. Deep learning, go for large amount of database, right? So without large amount of database, you may not be able to do the process with CNN, right? But when you go for the diagram on my right hand side, you can see that my data set 1 is brain image, data set 2 is lung image, but the size of the data set 2 is less. That means because brain image and lung image comes under the same category, I am going to derive some knowledge from the classification process of brain and apply it to my second process so that I can easily do that even though I have a less amount of data set. This is all about transfer learning. Now the question you must answer is what knowledge? I am talking theoretically. Knowledge. Practically, what is that knowledge? That knowledge is nothing but the filter parameters. The filter parameters. I told you in CNN, we have filter parameters to be adjusted and also the fully connected layer weights to be adjusted. But if these filter parameters are fixed, what are these filter parameters? They are feature extraction process. That means they are the features. If these features are fixed, then it will be easy for me to adjust only the fully connected layer weights. Why these features are fixed? I have an assumption that the features of the brain image will be almost, not exactly, almost equal to the features of the lung image. Right? So I need not train my filter parameters. The convolution layers can be fixed. Only the fully connected layer has to be adjusted. But we have a condition here. What is that condition? You cannot use an image. Say, for example, if you're using a brain image, you cannot use a model which has been already trained with aeroplane image. Aeroplane is completely different from your brain image. Aeroplane will have sharp edges, right? Wings and something like that. But when you go for your brain image, it is oval. It is a soft tissue type. So always make sure that when you go for transfer learning, many pre-trained models are available. The fixed parameter models are available. Check whether your image has been already trained with or not, or at least some similar images have been trained or not. If that is the case, you can go for transfer learning. This is the place, again, the scholars make many mistakes. They take some models, some random models, which is available in Python and MATLAB, and they may use for an application for which completely it will not suit. Then how will you get an answer? Your feature extraction is wrong. When your feature extraction is wrong, your complete process will be wrong. Based on this concept, we have many pre-trained models available. If you are using, you must be knowing about this: VGG16, VGG19, Inception V3, Exception, ResNet 50, and so on. If you take VGG16, what is VGG16? That 16 numbers corresponds to the number of layers. It is already fixed. The convolution layers are fixed. The pooling layers are fixed. You cannot change this. You can just drop down from the menu, click that, and you cannot change this. But if you go for a normal CNN, you can change this, but the complexity will be huge and you will not know how many convolution layers I should use and how many pooling layers I should do. Dense layers corresponds to the hidden layer in the fully connected network. Okay? So based on the experience, if you are choosing the correct pre-trained model, then the chance of your accuracy getting high is more than a normal custom. We have other models or images would have tremendously increased with the rise in the number of cases. We have both CT and X-ray, so it is suitable for transfer learning based approaches. It's available in DICOM format. You can easily download it. And this is the way how it will look like. Your COVID-19, your pneumonia, SARS image, everything looks similar. If I don't give the name below, definitely you will not be able to identify which one corresponds to which. So complex situations, don't think now the people are moving towards deep learning. So I also will go to deep learning. Research paper, when you write a research paper, try to give the